Hello everyone, my name is Bethany Sorenson and this is my presentation for my final project for ADTA 5550 with Dr. Nguyen. I'd like to begin with an introduction and overview of my project. My project explores the development and optimization of a convolutional neural network designed to classify images from the CIFAR dataset. My project includes exploring different aspects of CNN model design, training, and performance evaluation using Dr. Nguyen's lectures, as well as other academic sources available to me. My goal was to construct a CNN that balances complexity and efficiency to achieve high classification accuracy. Through the project, I experimented with various architectural adjustments, compared the performance of different models, and ultimately optimized weight initialization to enhance training stability and accuracy. First, I'd like to discuss the dataset that I chose for part 2 of my project. The dataset I chose is titled Natural Images, and I retrieved this dataset from Kaggle.com. The Natural Images dataset is a curated collection of 6,899 images spanning 8 distinct classes: airplane, car, cat, dog, flower, fruit, motorbike, and person. And as you can see here, I have included a collage of some of those pictures that could be found in this dataset. This dataset was created to serve as a benchmark dataset for research on the effects of degradations on deep neural network architectures. This dataset provides a diverse set of images compiled from various publicly available sources, making it a valuable resource for training and evaluating deep learning models in image classification tasks. Each class contains a significant number of high-quality images collected from well-known datasets. These images vary in background, lighting conditions, and perspectives, creating a diverse dataset for testing convolutional neural networks. The Natural Images dataset is a well-structured and versatile dataset, making it perfect for this project. Next, I acquired the CIFAR dataset from the link provided by Dr. Nguyen in the Datasets folder in Canvas. The CIFAR dataset is a widely used benchmark in computer vision, consisting of 60,000 color images at a resolution of 32 by 32 pixels. These images are divided into 10 distinct classes with 6,000 images per class. Out of the total dataset, 50,000 images are allocated for training, while 10,000 are reserved for testing. The dataset is further split into 5 training subsets and 1 test subset, each containing 10,000 images. Unlike the test subset, which only includes 1,000 randomly selected images from each class, the training subset distributes the remaining images in a randomized manner. This means some training subsets may have more images from one class than another, but overall, the training set maintains a balanced distribution of exactly 5,000 images per class. An important detail about the CIFAR dataset is that its classes are completely mutually exclusive. For example, according to Dr. Nguyen, there is no overlap between the automobile and truck categories. The automobile class includes vehicles such as sedans and SUVs, while the truck class is strictly limited to large trucks. Notably, pickup trucks are not included in either category. This strict categorization helps the model learn clear distinctions between object types, making this dataset great for this project. For my first model, I designed a CNN model composed of 4 convolutional layers, each followed by max pooling and dropout layers to extract hierarchical features while preventing overfitting. I'd like to take some time to talk about max pooling and dropout layers. They are crucial components of my CNN architecture and ensure that my model is both efficient and generalizable, preventing overfitting while maintaining strong feature extraction capabilities. Max pooling is a crucial component in convolutional neural networks, as it helps reduce computational complexity while preserving essential features. CNNs extract features such as edges, textures, and patterns by applying the convolutional filters. Max pooling addresses this issue by reducing the spatial dimensions of feature maps while retaining the most significant information. It works by dividing an input feature into small, non-overlapping regions, typically 2 by 2 or 3 by 3. By selecting the maximum value from each region, for instance, in a 2 by 2 maxing pool operation, a matrix of values is reduced by keeping only the highest value from each subregion. This process condenses the feature map without losing any key characteristics, ensuring that important patterns are retained while unnecessary details are discarded. The inclusion of max pooling in my model provided several benefits. It significantly reduced computational complexity by decreasing the number of parameters and operations required, making the model more efficient. This was especially important for a deep network where feature maps can grow exponentially without proper downsampling. Lastly, max pooling contributed to preventing overfitting by forcing the network to focus on the most prominent features rather than memorizing exact pixel locations, which can otherwise lead to poor generalization on unseen data. However, while max pooling played a role in preventing overfitting by reducing spatial dimensions, it was not sufficient on its own. Deep CNNs have millions of parameters, making them highly susceptible to overfitting, where the model memorizes training data rather than learning general patterns. To address this, I incorporated dropout layers after each max pooling operation. Dropout is a powerful regularization technique that randomly deactivates a fraction of neurons during training, ensuring that the network does not overly rely on specific neurons. This forces the network to distribute learning across multiple neurons rather than relying on a few dominant ones, thereby improving generalization. This effectively reduced overfitting by ensuring that no single neuron had too much influence on the learning process. This prevented the model from memorizing specific patterns and instead encouraged it to learn more generalizable features. Another advantage of dropout is that it acted as an implicit model averaging technique. Since the network effectively trained multiple different architectures during each iteration, the final trained model behaved like an ensemble of several smaller networks, improving stability and predictive reliability. The combined use of max pooling and dropout significantly improved my model's performance. Before implementing these techniques, my model suffered from high variance, where training accuracy was high, but test accuracy was much lower. Additionally, after integrating max pooling and dropout, the model became much faster, as max pooling reduced the computational burden. Overall, the use of max pooling and dropout played a vital role in enhancing my CNN's efficiency. This model was based on the model I did for assignment 4, as specified by the project instructions. However, due to CIFAR dataset being a more complicated dataset, the CNN was redesigned to be more complex for more complex feature extraction. The layers include a 64 filter convolutional layer with a 3x3 kernel and ReLU activation, followed by a pooling and dropout layer. Subsequent layers increase the filter count to 128, 256, and 512 respectively. To capture progressively more complex image features, the model was trained using softmax cross-entropy loss and optimized with the atom optimizer. The final test accuracy was recorded at 71.6%, indicating decent performance, but still room for improvement. I then compared the performance of my CNN model on two datasets, MNIST and CIFAR. The CNN model I designed for MNIST, which consisted of a single convolutional layer, achieved an accuracy exceeding 98%, whereas the CIFAR model, despite having more layers and filters, reached only 72%. This discrepancy is largely due to the inherent differences in dataset complexity. MNIST contains grayscale, uniform, handwritten digits, making it easier for a CNN to learn distinguishing features, whereas CIFAR consists of color images with more variation in objects, textures, and backgrounds, requiring a more sophisticated feature extraction process. Next, I aim to improve the CIFAR model's accuracy by first increasing the number of layers and filters, assuming that a deeper network would improve feature extraction. While this led to slight accuracy improvements, I researched alternative methods for more significant improvement. Research on CNN optimization techniques led me to experiment with weight initialization. I found that the He initialization, particularly suited for networks using ReLU activation like mine, significantly improved training stability by mitigating the vanishing and exploding gradient problems. Implementing He initialization increased my model's accuracy from approximately 72% to 82%, demonstrating the importance of proper weight initialization in deep networks. I'd like to discuss weight initialization and why this significantly improved the model. According to sources such as Medium and Geeks for Geeks, weight initialization is a very imperative concept in deep neural networks and using the right initialization technique can heavily affect the accuracy of the deep learning model. Thus, an appropriate weight initialization technique must be employed, taking various factors such as activation function used into consideration. Now, let's talk about weight initialization and why it played a significant role in improving my model's performance. In any neural network, including convolutional neural networks, weight initialization is a crucial factor that directly impacts how well and how quickly the model learns. Poor weight initialization can lead to issues such as vanishing gradients, exploding gradients, or slow convergence, making training inefficient or even preventing the network from learning altogether. This is especially important in deep networks where multiple layers depend on backpropagation to adjust weights effectively. Initially, my model used a standard weight initialization approach, but after analyzing my results, I realized my model's performance could be improved by optimizing the way weights were initialized. That's when I decided to implement key initialization, which is specifically designed for networks that use ReLU activation function. Key initialization is a method that ensures that weights are set in a way that maintains a proper variance throughout the layers of the network. This prevents gradients from vanishing or exploding as they move backward through the layers during training. The key idea behind key initialization is that the variance of each layer's weights should be scaled based on the number of incoming connections to that layer. This method is particularly effective for ReLU activation functions because, unlike other activations, ReLU does not naturally maintain a balanced mean and variance of activation across layers. Without proper initialization, some neurons may output values that are too large, leading to exploding variance, while other output values that are too small, leading to vanishing gradients. By using key initialization, the network was able to train much more efficiently and achieved significantly better performance. Before implementing key initialization, my CNN achieved an accuracy of around 72%. After switching to key initialization, the accuracy jumped to 82%, which is substantial improvement. This is because my network was now learning more efficiently, with gradients propagating properly through all the layers. The optimization allowed my model to extract features more efficiently, especially in the deeper convolutional layers where vanishing gradients were more likely to occur. Ultimately, I learned that choosing the right weight initialization strategy is crucial for optimizing your model. Key initialization was the best choice for my ReLU-based CNN. This highlights the importance of not just focusing on network or architecture hyperparameters, but also on how weights are initialized, as this small change can lead to major improvements in performance. From my experiments across all parts of the project, I derived several key insights. The complexity of a dataset significantly influences CNN performance. Simpler datasets like MNIST allow for high accuracy with relatively shallow networks, whereas complex datasets like CIFAR require deeper architectures and additional regulation techniques. Additionally, increasing the number of layers and filters can enhance a CNN's ability to learn hierarchical functions. But without proper initialization and optimization, diminishing returns or overfitting can occur. Lastly, weight initialization plays a crucial role in model training. Key initialization proved to be very effective, addressing gradient-related issues and ultimately leading to a significant accuracy improvement. This project provided me valuable hands-on experience in designing, training, and optimizing CNN models. By experimenting with different architectural choices, comparing different dataset performances, and implementing advanced initialization techniques, I successfully improved my model's accuracy from 72% to 82%. My future work could explore additional enhancements, such as fine-tuning hyperparameters, implementing more advanced data augmentation strategies, or experimenting with alternative optimizers. Ultimately, this project provided me deeper insights into the practical challenges of CNN training and performance optimization. Thank you.